podcast is brought to you by LMU Munich.
And good morning. Yes, I have been asked to, on this string physics school, to talk about experimental physics, about the status of particle physics, which is not only experimental in general, but is also theory, of course. But I show you the an experimental tour de force through the entire field. Of course, 1 hour is by far not enough to do this in all respects, so I had to choose a few things and had to leave out others. But I tried to be as general as possible and, of course, not talk about theory, right? Not much, at least. So, the title is Status and Open Questions and the Future of Particle Physics, which is quite a task. To make it even more academic, I have chosen to do the subtitles in Latin. And of course, the first you understand probably. If you don't understand Latin, I have forgotten almost everything I learned about Latin, but this means where are we? This means what is it good for? And this means where do we want to go to? And of course, the subsections are of different lengths. Now, just to give you an overview, it's a bit bright here, so you don't see the entire picture, but this shows one of the shots of the Hubble telescope into the deepest space. I think several thousand hours of exposure time for this picture, and every light dot you see here is not a star, but is a galaxy. So we see here almost to the end of the visible universe. The red dots are so far away that we see by eye the redshift. Now, of course, this shows already that one of the motivations to do particle physics, either theory or experiment, is connected to applications in cosmology. And if we look to this single graph, and I don't spend much time on it, it's taken from colloquium talks which I used to give. But just to give you the scale, the universe has a size of 10 to the 26 meters. This is just the age of the universe multiplied with the speed of light. It's not an entirely big number, as you may feel. And the smallest number we see here, after all these substructures, is quarks and leptons, which are today the elementary particles we have. They are point-like. They don't have a visible extension, at least not so far. And we know that if they have a physical size, it must be smaller than 10 to the minus 18 meters. So we span 44 orders of magnitude in our attempts of physics description of the world. And one particular number I would like to point out here is the difference in size between the universe and the atomic nucleus, which is 40 orders of magnitude. And that is exactly the difference in strength of two of the basic forces of nature, namely the strong interaction and gravity. Their difference in strength is about 40 orders of magnitude, and this sets the scale by the size of the universe. Okay? Of course, we don't know today whether the story will end here, but this is also a matter of time, how much further we could go. And of course, there are quarks and leptons. The question is whether they are really point-like particles or whether they are composite of something even more fundamental, but this we don't know, and this is one of the topics we want to tackle in the future. Okay, before we go to future, we have to take stock of what we know today. What is the status of particle physics and our knowledge of the world of particles today? Okay, let me start with something very simple, and of course all of you know this, but let me show it anyway. The standard model of particle physics is entirely easy, and it's even almost primitive, because we have gotten down to a number of 2 times 6 elementary particles, 6 quarks, 6 leptons, which you can sort in 3 families. And of course, what is missing here is the number is antiparticles, which each of these particles has its own antiparticle. With neutrinos, we are not so sure, because there's still the possibility that neutrinos can be their own antiparticles. Otherwise, the charged leptons here have antiparticles with just different sign of the electric charge. Now, this is much, much easier than in atomic physics or even nuclear physics, where the basic chart of the constituents of the theory is much, much more complicated, so we are here at a very basic level already. And we have elementary forces. We know so far 4 of them. 2 of them are in theory are even unified, the electromagnetic and the weak force. We have the strong force and gravitation. We have exchange bosons which mediate the forces between these leptons by these 4 different forces. The gluon for strong, the photon for the electromagnetic, 2 charged and 1 neutral boson in the weak interaction. And for gravitation, we say it's a graviton, although we have not measured the graviton by experiment so far. Now, the thing is that, and this I indicated already when discussing the first slide, if I put the relative strength of these forces to 1 for the strong force, then the electromagnetic is something like 100th, namely just the coupling, this Sommerfeld coupling constant. The weak force is 14 orders of magnitude weaker, and the gravitation, let's say between 2 protons at or quarks at 1 Fermi distance, is 40 orders of magnitude weaker than the strong force. And of course, the gravitation so far has played no role in practical particle physics. It's much too weak. But it plays a role, of course, in theory, and of course, especially in case of string theories. Now, the standard model so far describes the dynamics of all the known particles and forces which I have displayed here, where the known matter, we sitting here, and the matter around us just consists of the constituents of the first generation, while the higher mass generations of leptons, quarks and leptons, we just produce, and we know from particle collisions from collider experiments in general. Now, this picture is not entirely complete. It's a basic standard model, but the standard model is lacking one part, namely theoretical predictions to explain the origin of different particle masses. All of these particles have different masses. As we know now, since a couple of years, all the neutrinos have masses. And in the bare standard model, of course, neutrinos are massless. So we have some signs of beyond the standard model physics. And one ingredient which is also missing, which belongs to the standard model, is this prediction of the origin of masses. This, for instance, the most en vogue theoretical extension or part of the standard model is the Higgs mechanism, the Higgs boson, which is predicted by the theory then, but its own mass is not predicted, and we have not observed this so far. So one of the major challenges for the future, which has already begun, as I will show you, will be to find this Higgs boson if it exists. All right, I am going to show you a few results, or summarize some of the major results of the last couple of years of experimentation and also of theory, of phenomenology developments and predictions and fits to data. One is going to CERN, since we are here in Europe, go to CERN. The CERN site is close to Geneva. Geneva is down here. This is the international airport. This is the French mountains already. So this white line is the border between France and Switzerland on the other side. This is the CERN main site, which many of you may know. It's just across the border. It also has an extension here because there are big accelerators. For instance, the old, almost ancient SPS, superproton synchrotron, which is nowadays a pre-accelerator for the large one, for LHC. But what is shown here is that this 27-kilometer underground tunnel, which is sketched here, was called LEP in previous years. So it was built for LEP, an E plus E minus collider. It was taking data from 1989 to 2000 when it was switched off and converted into the Large Hadron Collider. At LEP we had 4 experiments, and I will show you the summary of the most important results from LEP first. And then, of course, we also have to take care about, oops, I was a bit too fast, about the LHC, which has now been built, and PP collisions up to 14 TeV are planned there. It went into operation in 2009 after recovery from a 1-year repair of a major accident. And since 2010 we have highest energy collisions in the world. And here we have 4 experiments also, but distributed a bit more asymmetric. We have two big ones, Atlas and CMS, two large multipurpose detectors, and two more specialized detectors, LHCb and ALICE. All right, let me give you some highlights from the time of lab, which means it's basically the results we achieved at the end of the last millennium. And I think one of the very early highlights when the lab was switching on was already visible after a couple of weeks or months of operation, and then after some time scanning the center of mass energy of the E plus E minus collision, which is plotted here around the C0 mass. We got this resonance shape measurement of the line shape of the C0, and the three curves here are predictions by the standard model for the case that there are 2 generations of neutrinos, 3 generations of neutrinos, or 4 generations of neutrinos, and you can see that the data very significantly pick out the one choice, namely that there are only 3 generations of neutrinos. From that time on, we knew that there's most probably no 4th generations of quarks and leptons, except it would be heavy, very heavy neutrinos which would be there, which is unlikely. And the fit to this data gave a number which is very, very close to 3, but if you look very carefully, you see it's 2 standard deviations apart from 3. So there may be something which was not in the theory, but which seems to be in the data, but it's not very significant. Of course, 2 standard deviations you can have by all kinds of systematic uncertainties. I think this was one of the most important measurements, and it came very early. Then there was the precision of the entire large collider. It was one such that the mass of the C0, which is just the peak of this resonance line, could be measured to 25 parts per million. This is the number, 91 point something GeV. The accuracy here is one of the most accurate numbers known from particle physics measurements. And in order to appreciate that the experimental challenge was not negligible to really measure this thing, even when the accelerator was built, is that one could get this precision only after correction of the data for the phases of the moon and for the train schedule of the French TGV, which is stopping here somewhere in Geneva. And while this sounds a bit odd, the phases of the moon give contraction and expansion of the crust of the Earth. And this changes the entire size, the circumference of the lab tunnel by a few millimeters. And these few millimeters change makes, of course, a longer traveling time of the beam. And if one does not correct for that, then one gets the beam energy not right. And so the accuracy one had to reach was a factor of 5 larger than this number here, which was due to the phases of the moon. But then after this correction, there were still occasional jumps in the energy, which were for a long time unexplained until somebody was reading the TGV train schedule and finding that every time when the TGV leaves to Paris from Geneva, the apparent energy of the lab collider changed by an amount which is about this size. And after correcting for that, where does it come from? Of course, it's the TGV is a constant current machine, and so the back current flows down to the Earth, and it diffuses into the crust of the Earth and changes the magnetic field of these magnets in lab. So one had to correct for that. Okay, now we know this number. What we do out of this, I will show you in a minute. We had many other experimental tests of the standard model of particle physics at per mil level. While this was parts per million, most of the other measurements were at per mil level. One thing in strong interactions, for instance, these red points are measurements of alpha S, the coupling constant, coupling strength of the strong interaction. And this is predicted to depend on energy. It's not constant as all the others. They are also not constant. And it has this particular predicted logarithmic fall off with increasing energy, showing asymptotic freedom at infinitely high energies. And with the lab measurements and lower energy measurements, we could prove that this prediction of asymptotic freedom and also of confinement to the other side where alpha S explodes are correct as predicted by the gauge field theory of the strong interactions quantum chromodynamics. And whenever such a thing happens, that something very fundamental has been predicted and has then been measured, there is a Nobel Prize sometimes behind it, and this was the case in 2004 where CO is predicting the asymptotic freedom, writing it down for the first time 25 years before we're receiving this Nobel Prize. Okay. Then Leb was, of course, also looking for the Higgs boson. It could not find it. Direct searches made an exclusion that the mass of the Higgs must be larger than 114 GeV, and the precision fits to the electroweak data and radiative corrections, which were supplied by COE, showed us that the Higgs is most probably there, and then it has a mass which must be smaller than 185 GeV. All right, then all the other measurements at Leb are the mass of the CeV had, its total width, its hadronic cross-section, the ratio of leptonic to hadronic final states, forward-backward asymmetry of B quarks, then the polarization asymmetries, and other measurements, which I don't go into detail here. Also here, a polarized asymmetry measured as SLC, the linear collider at SLAC, the sine squared theta W, the effective one, the weak mixing angle. Then also the mass of the W was measured at Leb, at threshold, at much higher energies, and also its width. And the mass of the top was not measured by Leb because the top turned out to be too heavy to be produced. It must be produced in pairs, so you need 340 GeV, and Leb only went up to 209 GeV. But the top made radiative corrections which could be determined by Leb data. So what you see here are the measurements, the measured values with their error, and the fit of the standard model to all these data, and then the prediction of the standard model of these different values. And you see there are very much good agreement. This is shown here in this bar chart, where you have the disagreement, where the difference between the measurement and the predicted value in numbers of standard deviations, so the errors are taken into account. And you see that most of the predictions are within one standard deviation. There's only 3 out of about 15 or 20 measurements where one standard deviation is exceeded, which is just explained by statistics, by the law of statistics. So there's no signal of new physics. Even that one, which almost reaches 3 standard deviations, which is the forward-backward symmetry of B quarks. There's a slight difference here of 3 standard deviations. Even one such measurement you would expect in about 20 of such observables. So there is probably no sign of new physics, and standard model works extremely well. Concerning the Higgs search, this I mentioned already. This is the exclusion or the signal plot for the Higgs mass plotted on the x-axis, and these curves give the fit to the electroweak precision data of Leb, the ones I showed you in the charts before, just for different Higgs masses, and it gives a delta chi-square in the fit, which has a pronounced minimum around 90 to 100 GeV. These different curves depend slightly on different values of radiative corrections which are put in there, and fits to lower energy data maybe. So you see there's a slight scatter of that. The blue band gives the error of one such fits, and the minimum is at around 90 GeV. From that one can exclude the mass range, the mass range to the top, that the mass of the Higgs must be smaller than 186 GeV. This is something here at standard deviation, 4 standard deviations. And the lower bound is done by this yellow exclusion limit, which comes from direct searches for produced and decaying Higgs bosons, which have not been seen at Lab. And from that, a mass exclusion could be done, that the mass of the Higgs must be higher than 114. This little yellow band here is the newest result from the Tevatron, which just at the conference of last week, the ICHAP at Paris produced this value, or presented these values, that the mass of the Higgs is excluded in this mass window of 158 to 175. So you see, if we take all the theoretical fit serious, and of course the direct search, then the phase space for the Higgs mass boson is getting very tight. It's probably not at the high end of this mass range. It's probably, if it's there, at the lower energy, at the lower mass, which also the minimum here at the lower masses points to. And this is very difficult to find there. As we will see, LHC will take a couple of years to make this mass range visible. Okay, that's the status of the Higgs search. Let's leave for a second collider physics, and let me give you two examples of very nice results which really changed our image of particle physics and our knowledge during the last couple of years. And let's have a quick look at neutrino physics. This is a look into the Super Kamiokande detector, an underground large vessel having 50,000 tons of water as a target. And this is almost filled here. You see a boat with people just maintaining these phototubes, many thousands of phototubes, looking into this volume in order to find muons from cosmos, from atmospheric muons coming from particle interactions high up in the atmosphere. And now, what have they done there? Let's see. Oops, wrong direction. First of all, let me show you how they see and can differentiate between electrons running through this volume and muons, probably from atmospheric muons. You see that muons give a very distinct, almost ring-like signature in the volume of this detector, while an electron also gives a ring-like signature which is more fuzzy due to the electromagnetic shower which develops in the water. One can disentangle between the two. Now, what has been done there, and this is of course a couple of years ago since we know this, atmospheric neutrinos, one could see oscillations, one could find evidence that muon neutrinos go to another flavor of muons, which could not be, could be electron or tau or whatever. So this is the original plot in the plane of sine squared theta, the mixing angle between neutrinos, nu to something, and the mass, the difference of the squared masses of these two neutrino species which are oscillating, because if neutrinos are oscillating, they must have mass, even if it's very small. And you see it is apparently small, so the difference in masses squared is somewhere between 10 to the minus 3 and 10 to the minus 2. And these are the confidence limits of 1, 2, and 3 standard deviations in this parameter space, which has been given by this experiment. So we have maximal mixing angle and a mass difference of a few times, 2 times 10 to the minus 3 electron volts. That, of course, showed for the first time that neutrinos have mass, and there's, of course, a Nobel Prize connected to measurements like this. Now, nowadays, this is a bit historic, but since then we have a lot of more measurements by Kamiokande itself, higher statistics, better regions to include here. And we also have measurements from solar and reactor neutrino experiments, which then saw oscillations from the electron neutrino species to something else, maybe muon, maybe tau neutrino. And this also gave the solution to the solar neutrino problem, which was standing since many tens of years, that the neutrinos measured coming from the sun were almost by a factor of 2 less than expected from the energy bill of the sun. And this was then also explained by solar and reactor neutrino experiments more recently, which showed that there's also oscillation going on. Now, trying to summarize all this oscillation business, this is a nice chart. You can talk hours on that alone. It takes all the measurements. These lines are exclusion lines, and whenever something is filled, it gives a positive signal. So there was generations of experiments excluding more and more this mass squared difference. If there are oscillations, so there have no oscillations been seen, and then came super K with this 90% and 99% confidence level blob here, which we saw before in that plot. And there's also measurements from solar and neutrino experiments, Kramland, for instance, SNOW, also super K, very old ones like chlorine and gallium experiments. And they boil down that there's several regions now for the different species which we can identify. There is this 10 to the minus 3 from super K, which is the oscillation of the muons, atmospheric muons. And there's this blob here at even smaller masses, delta m squared, coming from solar and reactor neutrinos. And there may be further solutions, but with these two, one can already get a rather nice picture of the hierarchy of the mass and flavor eigenstates of 3 neutrino families. It may look like this, that one has a smaller mass difference here between electron and muon neutrino oscillation, and a larger mass difference from the atmospheric muon oscillations, probably to tau. And then one can also explain to how much these mass eigenstates consist of the different flavor eigenstates of electron, tau, and muon neutrinos. However, we are not sure whether this can even be an inverted hierarchy. So this is again an open question here, but lots of progress during the past few years. The next example I want to give is not at high energy or at no accelerator physics at all, but using precision experiment at low energies. There's many. I just show you one, which is very famous. This is the muon G-2 collaboration at Brookhaven. It's a rather small number of people. I don't show you the picture of one of the LHC collaborations because at LHC we are so many in the collaboration that they would not fit in all the seminar rooms which are here in this building. So this is a very small collaboration. This is a small storage ring where they stored muons and measured the muon anomalous magnetic moment. Just to give you a clue how this works in principle, one starts with protons hitting a target, giving lots of pions. Pions are decaying to muons. The muons then will be cooled a little bit, put in the same phase space. Muons have, of course, spins. Due to the decay kinematics, they all look to the same direction, just the direction of flight in the beginning. Then they are fed into this storage ring where they do several turns before they decay. And the clue is that the magnetic field they are subjected to is extremely well defined experimentally. And then one has, of course, spin precession, and if there's a deviation of G-2, then the spin will slowly depart from the direction of flight. And then when the muon decays, the electron coming out due to kinematic reasons decays in the direction of the spin. And here are detectors, many of them, precisely measuring the time and the direction of these decays. And so one can get back and calculate through the spin precession exactly the deviation of G-2. Now, it's a very small number which is measured here. This is an old previous value. Let's look at this more recent one. This is a number times 10 to the minus 10. So this is a very small deviation from G-2, which is explained by theory from radiative corrections. The experimental measurement is accurate to 0.5 ppm, which is an enormous precision, which can be obtained here. These are the measurements of this residual, these three last digits here, from positive and negative muons and its average. And here's the prediction from theory. Now there's two, because theory has also to take into account some measurements, namely the structure of cross-section at very low energies, the plus and minus, and from tau decays. And there are two different, they are slightly different. They are compatible with each other, but they are different. And, sorry?
How will you take these corrections to the theory aspect? I suppose if I calculate, do some order in perturbation theory, I get some number. Find a number, not this range. So I suppose they must be just point.
There's the hadronic correction to the fine structure constant. And that has input from experimental measurements, from the shape of the cross-sections integrated over lower energies. So there is an input from experiment in there here too. Yeah. So the difference between these two is experimental, right? But since they don't hardly, well, they agree, but they deviate a little bit, the question is this a theoretical uncertainty or is it an experimental systematic? We don't know. We just have to take it. But the upshot is many people, well, there are two parts of people fighting partly against each other, namely the friends of this number and friends of this number. And the friends of that number, I think, outnumber those ones, which doesn't mean anything, I guess. But if one takes this difference, it's almost at 3 standard deviation. Now, this does not give a signal for new physics, but it could be the first hint for new physics. I just show it here because it's one of the few examples where we have a 3 standard deviation possible disagreement to the standard model predictions, which by itself is not a signal yet, but it could be an interesting hint. And it does not come from high energies, it comes from very low energy, but precise experiments. Now, talking about extensions of the standard model, supersymmetry, I don't give an introduction. Supersymmetry, I guess, as string theorists, you are very firm in that. Now, supersymmetry is, of course, the extension of the standard model, which is pursued worldwide. And it makes many predictions, although the phase space of range of predictions of supersymmetry is extremely large because it has many, many free parameters which must be determined by experiment and cannot be determined by theory. Now, this is an attempt to take the electroweak precision measurements, which I have shown you in one of the previous graphs, which has a good agreement with the data, with the one exception in the forward-backward asymmetry of B quark at lab. And this has been fitted to the standard model, which is basically the numbers I showed you before, just a couple of years earlier, so not exactly the same numbers. Again, number of standard deviations 2 and 3, and here also to the negative side. The standard model gives a chi-square of 27 per 16 degrees of freedom, which is not excellent. It's just a probability of a few percent. Now one can take the minimal standard supersymmetric standard model, and this is the blue bars, and you see it fits, in generally it fits a bit better than the standard model, sometimes a bit worse, but all in all it's a better chi-square, which is much closer to 1 per degree of freedom, so the probability for the minimal standard supersymmetric standard model is a bit higher. And there's a third one, this in green, which is a constrained minimal supersymmetric model, which gives a chi-square in between. Now, from these numbers, you could not include, say or conclude that there is a hint for supersymmetry. There may be a very slight hint, but it's not very significant. And in most of the observables, there is no big improvement by supersymmetry. So we stay with our conclusion that the standard model is working just fine. There's just this one measurement here of the anomalous magnetic moment of the muon, which I showed you in 2 slides before, which gives indeed a very good chi-square if I include supersymmetry, even the constraint model, and so these differences in chi-squares should basically come from this one observable. So there may be hints, but no proof that there's anything new. So we say there's slightly improved fit quality of SUSY models, but this is mostly due to this one measurement, which is not fully understood at the moment. And this may be a hint, but certainly no signal of new physics. Okay, so summarizing up to here, where are we? Now, as I told you, there's no significant signal for physics beyond the standard model. We have a few 3 standard deviation things, but that is not called significant. And discovery of a new effect must at least exceed 5 standard deviations, and we have no single measurement like that. So standard model is just fine. However, the future has just begun. Namely, LHC has just started running, and I should not go out of this lecture without showing you at least the status of LHC and the first results, which have been presented just 1 and 2 weeks ago at Paris. Yeah, the LHC has finally started. This was a big happening. This was basically in March of this year. That was the start of high energy collisions. At the end of last year, LHC started already with collisions at injection energy, which was 900 GeV in the center of mass. Now we are at 7 TeV, and this is the highest energy ever reached at any accelerator in the world. And of course, the joy was just there. This is a picture of the Atlas control room just at the moment when people saw the first high energy collisions. Now, what is the Large Hadron Collider? It's not readable very nicely. Well, it's a proton-proton collider. I just go through this very quickly. We have 2 rings of proton accelerators in one machine. They are steered at 4 interaction points on top of each other. We have protons of about 10 to the 11 in each of the proton bunches, and we have along the machine up to 2,800 bunches in each direction. So their distance, because LHC has a circumference of 27 kilometers, is 7.5 meters. Since they move with the speed of light, we have collisions every 25 nanoseconds. So 40 million collisions per second at each of the interaction points. The luminosity is the standard luminosity, the maximum to be reached should be 10 to the 34 per square centimeter in second. At the moment we are 3 to 4 orders of magnitude below that value, but still ramping up very steeply. So we have proton collisions with 40 megahertz. We have more than one collision per crossing because of the density of these bunches. We have multiple interactions. At this high luminosity, we expect about 20 pp interactions per bunch crossing. So we have a collision rate of 10 to the 9 per second. Each collision gives many charged particles. So at any time in the detector, we expect 1,600 charged particles, which looks like this sauerkraut stuff like picture. And this means we have very high demands, of course, on detector and on data acquisition and data analysis. Now, the LHC is surely the largest scientific project ever attempted. There are 30,000 tons of 8.4 Tesla superconducting dipole magnets, which you see here in this picture in the background, which keeps the beam on a circular path. These magnets are superconducting. They are cooled down to 1.9 degrees Kelvin by 90 tons of liquid helium all over the machine. So we have a big part of the available liquid helium in the world always in the LHC. And 1.9 degrees is even below superconductivity. It's so low that the helium, liquid helium, is even superfluid. That means it flows through all these pipes in the ring without any mechanical resistance. 40 megahertz collision rate means 1 terabyte per second raw data from any of the two big and all the small experiments. 1 terabyte per second is quite a good word. That's more than the entire telecommunication traffic on the entire globe coming out of one detector here. And there one has to do, of course, quite tricky things to cope with this enormous amount of data. There are two multi-purpose detectors, Atlas and CMS. I'll show you a picture of each of them in a second. Atlas weighs 7,000 tons. CMS, the C stands for compact. It's much smaller than Atlas. Nevertheless, it weighs much more, almost double. And this is not just that material. This is all made out of high precision particle detector technology. For comparison, the weight of a fully loaded Boeing 747, I should replace this with the 380, 747 is slightly outdated, 200 tons. The Eiffel Tower is a bit heavier than Atlas. Of course, Atlas looks much nicer than the Eiffel Tower. And a warship, typical big warship, has something like 8 to 10,000 tons. Now, this is a view to the tunnel. Almost 5 years ago, when the tunnel was equipped, but the magnets were not fully connected. Now it's a pity that the light does not go down a bit further. Here one sees the connections between two dipole magnets. Each magnet is 15 meters long, high-tech product developed at CERN, made in industry. And of course, these superconducting wires have to be connected somehow. Now, if you never have asked the question, how do I connect superconducting contacts? You may look into the history here. Anyhow, these are the filaments, the slices of the superconducting cable coming out here. They must be soldered together with a special technique in order to make a zero, and zero really means 0 nano-ohm contact, because otherwise these many thousand amps which flow here would destroy these cables immediately if they would have an ohmian contact. What happened in 2008 when the machine was ramped up first was that at one place like this, there was an insufficient soldering done due to, somebody didn't pay attention probably. And it had 200 nano-ohms of resistance. Now the current flowing through here warmed it up. Then when it warms up a little bit, it falls back into normal conductivity, which is called quench. And then the entire energy just dissipates in this ohmian contact, which goes into micro-ohms or even milliohms only. And this was enough energy to blow up the entire region here. It was more or less exploding, ripping apart the helium transfer lines, exposing helium into the vacuum inside these pressure values, these pressure barrels of the magnets. And this expansion waves then ripped apart parts of the tunnel and of these magnets, which caused one year of repair afterwards. Okay. Now this has all been improved. This is a front view of the Atlas detector in 2006 when it was not fully assembled. You see people down here to appreciate the size. This is 25 meters in diameter, and Atlas is 45 meters long. The beam pipe will run through here and through the center, and there is this onion-shaped shells of different high-precision detectors. In the outer shells, you see the giant muon chambers measuring muons coming out of this whole structure, and these giant air core toroid magnets, which make a circular magnetic field here at the location of the muon chambers in order to measure their momenta. Next picture shows CMS with a fisheye photograph taken. Again, there are people here on the balcony, and one of these huge wheels, which has a diameter of 14 meters, so it's smaller, more compact, but heavier, have just been lowered down here. I think it weighed 2,000 tons, so it was a very tough operation. Of course, from these two detectors, you don't see much anymore today, because they fill up the entire cavern downstairs, and even if you are allowed to go there, which normally is not the case, you just stand with your nose in front of detectors, you don't see much. Okay, to the physics potential of LHC. This is a summary of the sensitivity to the respective Higgs mass, standard model Higgs mass here from 100 to 1000 GeV, and these colored lines give you the sensitivity for an integrated luminosity of 100 inverse femtobarn, which is several years of Atlas running at the highest luminosity. We are not there, clearly. And for discovery, you need a signal significance, which is plotted here, of more than 5 standard deviations. And you see different final states add in different kinematic regions, but if you measure them all, one can get such an exclusion, such a sensitivity line after a couple of years of running for different Higgs masses, and you see it's everywhere significantly above this discovery limit of 5 standard deviations. So the conclusion was, or still is, if the standard Higgs model, the standard Higgs exists, and COE standard model tells us if it exists, its mass must be less than 1 TeV, then it must be found at the LHC. Or if it does not exist, then, or if it will not be found, then it means it does not exist. And then, of course, this may be even more interesting, but not very spectacular, of course, to sell in public. Now, the second thing is SUSY discovery. I don't go into details of all these plots because it would simply take too much time. If you know these plots, you may remember that with a certain luminosity, even a couple of years of running, you can exclude squark and gluon masses always in this region. And here is supersymmetric mass scales is plotted here. And you see one can exclude these masses or find them, if they are there, up to several TeV in mass even. Now, if there's supersymmetry, if it's not in a very, very odd corner of phase space, also supersymmetry should be found at the LHC, and the first signatures should be there already much, much earlier than for the Higgs. Now, what has LHC done so far? Well, I said it started on the 30th of March with a very low luminosity. So this is the integrated luminosity, the integrated number of collisions, so to speak, explained here in inverse nanobarn. There was a very slow decrease in the beginning, and then, of course, things improved, and you see we are now on a steep rise. This is just a couple of days ago, almost doubling the entire statistics of the last couple of months in the next 2 days. Until we have reached, hopefully soon, something like a design luminosity. So far delivered by the machine is 360 inverse nanobarn, and about 340 have been taken by experiment. This is the yellow part. And you see the experiments are fully there. If the LHC is running, they are taking data with almost 100% efficiency. Now, what have we seen at LHC so far? Very early in the beginning, after the first few collisions, we already identified the first W decay. A couple of days later, we needed more statistics. The first Z decay. We saw the first top quark candidate already in May. It's a candidate. I mean, one needs more statistics in order to really say one can see the top quark. And that was the first time a top quark signature has been seen in Europe, by the way. So far, tops have been exclusively produced at the tevatron. And then here is, this was about here was the time of the highest dijet mass event, which I will show you in a few seconds, which has been taken by the ATLAS detector. This is all ATLAS. CMS has similar shapes, and I don't double the things I show you here. Now, the official data, the overall data taking efficiency, as I said, is close to 100%, which you can see here. And the yellow part is always full detector on, so there is nothing missing. The full detector is operational rather beautifully. The peak luminosity so far is just a little more than 10 to the 30. I remind you that the peak luminosity to be reached with this machine should be 10 to the 34, so there's still 3 to 4 orders of magnitudes to go. The luminosity today is known to just 11%, and the error is dominated by the knowledge of the beam currents. This will also improve if we have more statistics. Now I show you a little movie, which is an animation of the first, one of the first collisions we have seen. Yeah, the tunnel is pretty dark. I don't get it darker. The collision event which will happen is not an animated one, it will be a real one which has been copied into this movie. So this is a picture of the inner tracker done in silicon technology, and of course the outer shells have also seen that, and it's now a kind of routine. Let me show you a few events. This is a very much blown up picture of one beam collision where we have measured four interactions clearly. You see this by the extension of the charge tracks, which are measured in the silicon pixel detector, which is just a few centimeters from the beam line. And by extrapolating back these tracks, now you see there's a lot of, you get many of these hits, and you need quite some computing power to do this assignment of the different hits to the different tracks, but one can do that. And then one sees here that there have been four basic collisions, which one can, however, disentangle with these super sensitive silicon vertex detectors. This is a full view in the full tracker of this event, and this snapshot is just a little part from the center. So that's what we call pileup. We expect at the peak luminosity of 10 to the 34, we will have about 20 of these in each of the bunch crossings. Yeah, what we are doing now is probably not seeing new physics, but what we are doing is the rediscovery of the standard model. Parts of these measurements we have done 20 years ago at the previous machines, at the SPS, and also, of course, at the tevatron. Here's one example. This is a dimuon mass plotted of many events taken. This is dimuon mass, and what one sees is, of course, a resonance structure here of several particles at low masses, the rho, the omega, the phi, the j psi, the psi prime, then the epsilon, the BB bar resonance, and then it falls down, and this is even the peak of the C0 decaying into muons. We have about, I think, 50 or 70 events sitting in here, making the first measurement of the cross-section. Of course, this is all no new physics, but it's very important to see these things in order to find physics extending the standard model with higher statistics. This is brand new data. These data have been taken up to 3 weeks ago, and they are already in this plot. If one magnifies this region around the epsilon resonance, one can see that there's not only the epsilon resonance, but probably the epsilon 1s and the 2s can be seen here, can be statistically fitted, and one can even get a number of events of these different resonances. So the detector is performing quite well. Let me show you this one real event taken by ATLAS in a computer simulated display. This is the C0 decaying, lots of stuff in the central detector here, and then in the outer muon chambers you see in the forward direction a high energy muon and one in the barrel. And if one does this mass calculation, these have an invariant mass of 87 GeV, uncalibrated. So this is probably a C0 decay, one of those sitting in the C0 peak I showed you in the transparency before. Now with these now about even more than 100 candidates for the zeros. One can do the first cross-section measurement at 7 TeV. This is the center of mass energy, so the previous experiments are here, namely tevatron, and even older experiments, UA1, UA2 at the SPS. The red line, well, they have been PP bar. This was proton-antiproton, and the predicted cross-section would be this dotted line. Now for PP, which is LHC, it would be lower at lower energies, but approaching the other curve here. This is a measurement of Atlas. CMS has a similar one. So we see the standard model again, and it's very assuring to see the first data coming up here. Now, looking for new physics, you want high energetic jets. And this is one of the hardest jets seen at the LHC. It has a PT of 1.1 TeV, measured here in the calorimeter. One hardly sees this histogram here. This is an event display. There's lots of jets. In this, you see 2 jets, but there's many behind each other. It's at least 4 one can see here. And this is in the energy flow. You see 4 high energy jets, one with more than TeV. And of course, such things could be signatures of decaying new heavy objects. Now, this is a measurement of the PT jet distribution of hadronic jets measured so far as a function of the PT. And you see this, the yellow is the theoretical, the Monte Carlo prediction of the standard model. You see the data is in very good agreement with it. Of course, this last bin consists of one event, right? This is the one event sitting in here. We should have seen a tenth of an event all now. So this is, of course, no signature for new physics, but if we have 10 times the statistics, we would be already sensitive on the TeV scale for new physics. Now, one thing we could already improve existing limits. This is a search for excited quarks, namely excited quarks decaying into 2 hadronic jets. And what one studies here is the dijet invariant mass plotted here from 500, 1000, 1500 GeV. These are the data, the dots, and the standard model fit is the full line, which is perfectly in agreement with the data. And now one can see for small hints of little peaks for a squark, for instance, of mass 500, 800, and 1200 GeV. You would get a small structure here. This is Monte Carlo, of course. And from the absence of signs of that, one can do a statistical calculation up to which mass can one exclude these heavy quarks existing and decaying. And this upper limit now is from Atlas with this handful of data only we have so far, a few handful, of course, that the masses are excluded in the range from 400 GeV to 1290 GeV at 95 confidence level. And this is already better than the last publication from tevatron. This we can do with little statistics because we have a much higher energy range than the tevatron. But you see the potential, and there's more to expect it in a couple of months. Now, summarizing, where are we? The standard model of particle physics describes the unified electroweak interaction and the strong force with gauge-invariant quantum field theories. It is extremely successful in consistently and precisely describing all particle reactions which we have produced and observed so far. It shows no significant discrepancies. There are a few small discrepancies, but no significant discrepancy between data and theory. However, it leaves open fundamental questions and problems which cannot be answered by the standard model, and that leads us to the next part then of my talk, which we are pretty advanced in time, I see already. Where do we go to? But before we do this, just a few slides on why should we do this. So what is particle physics good for? Now, I don't tell you too much here. I just want to show a few things. There was, which I found very interesting, a CNN contest now a couple of years ago, which asked people what, to your mind, are the greatest wonders of the modern world. Now, what do you think are the greatest wonders of the modern world? 50% of people responded with the World Wide Web. Okay? And then the second place was held by particle accelerators at CERN. Now, this was an international contest, right? And this is 16%. Quite remarkable, because the World Wide Web, of course, is also born at CERN at the time when LEP was done, right? So particle physics is shaping the world. What we are doing is apparently also interesting to people. Yeah, on place 3 there was none, no wonder of the world. Then there was Dubai, the bionic arm, and the Three Canyon Dam in China. And of course, the list extends. I just stopped it here, but it's remarkable that particle physics takes the first two places. Okay? Now, just a commercial. I think you know this all in basic, but I have used this transparency in many places. What is particle physics good for? It is, well, first of all, it's a knowledge-oriented basic research. So you don't ask immediately the question, what does a man on the street have gains from particle physics results? It has no direct relation to everyday applications. However, it bundles scientific interest worldwide and avoids duplication of projects, which I think would be a good thing for many fields, spending money and doing research. It initiates technological and theoretical developments at the limit of feasibility, and many of spin-offs in technology and theoretical developments have already reached many other fields down to the everyday life. It provides significant spin-off of these technologies, for instance, in medical science, in engineering, and in other natural sciences, and also in culture. It provides a comprehensive scientific education of many people, young people, in an international and competitive environment. You should be able to judge this much better than I can. Just an example of one of the other fields which is inherently connected to the knowledge of particle physics, and that is cosmology. Now, this is a German slide. I thought I should train your German skills a little bit at this thing. Many of these things you will, however, understand. You know, this is a timeline going from something which may have been the Big Bang to our time, which is now 13.7 billion years after the Big Bang. It gives you the temperature at the universe at that given time, and you see it's terribly, it's double or triple logarithmic. So the very early times in the universe are much enhanced here. There's many, many interesting things happening, like quantum gravitation, the big unification, inflation, the generation of asymmetry between matter and antimatter, the disappearance of antimatter after 10 to the minus 10 seconds, and all what was left is the world we are made of. Formation of protons and neutrons out of the quarks. Then the positrons annihilate, and only a little rest remains of electrons after 1 second. Then there's a nucleosynthesis of helium. And much later, the formation of atoms, and namely when the universe becomes as cold as 1000 Kelvin, which is the case after 300,000 years. Then instead of charged protons and electrons in a plasma-like soup, charged neutral hydrogen atoms and helium atoms form. The universe becomes transparent. That is exactly the time we measure the asymmetry in the background radiation so far, and we know all the cosmological details of the couple of years. The last couple of years, they come from pictures taken at that time, which we may look back. And then much later, there's the generation of stars, and only in stars we can make heavier atoms. So this happens only after 1 billion of years. The first stars form, build heavier elements. The first supernovae appear, blowing out the heavier elements into space, making eventually planets where human beings like us are now looking at it. So now particle physics, of course, makes all the unknown and known part down here, and without the knowledge we would have of the standard model in particle physics, I think the whole picture in cosmology would just not be what it is today. Just to demonstrate what astrophysics and astronomy can do, they can look back to this age. Partly we did this in one of the first pictures I showed you of the Hubble, when we showed where we look at the first galaxies. Now this cosmic background radiation goes back to that point where the radiation became free, and that's the end of experimental studies in astronomy. If you want to know more details, like for instance particle physics and LHC, they reach down to energy densities corresponding to an age of the universe of 10 to the minus 15 seconds. Then of course we have to extrapolate further. Now, particle physics is very important also for other fields like cosmology. And now let's just have a few slides and seeing where do we go to. Now I mentioned, of course, the entire field is motivated, highly motivated by the success of the standard model, but also by the open questions which are left open by the standard model, and they motivate going on further. Now, one of the most fundamental questions is what is the origin of mass? Does the Higgs particle exist? And if not, what is the mechanism of electrotropic symmetry breaking, which may be even more exciting, as I said, but probably not for our funding agencies if we say we found nothing, and that is very exciting. I showed you this Higgs graph already. So we have a small phase space left only for the Higgs mass of the standard model. It's probably not far above, and it's, if it exists, it's probably in this little band here, which turns out to be rather difficult also for the LHC. Will take a couple of years. Now, another very basic question is, why are there 3 families of quarks and leptons, not 4 or 2 or only 1? And the next question then is, why is the electron charge thus just exactly the same size of the proton charge, but with another sign? If that would not be the case, then the universe would not be electrically neutral. Electromagnetic radiation would not be able to travel through the universe, and our universe would look much, much different. We would not exist because the electromagnetic force would dominate instead of gravity. Where's the antimatter in the universe? A very big mystery, which we have to explain. We have tried to measure CP violation in particle reactions. In the quark sector, we have found it, but it's much too weak to explain the degree or the amount of matter which is existent in the universe without being counterparted by antimatter. Next question is there one universal fundamental force, something like grand unified theories? We have hints for that, like plotted in this picture, where there is the collision energy or in GeV, 10 to 5, 10 to 10, 10 to 15 GeV. And this is the inverse of the coupling constants of the electromagnetic, the weak, and the strong force, so the inverse. Yeah? That's why they are upside down. And this is their predicted energy dependence in the standard model. And they don't hit each other at one point. However, if one introduces supersymmetry at a TV or so, then one gets different slopes and they would fit into one point. And what people usually neglect here is the fourth force, namely gravity. Now, since this is the inverse, gravity would be infinite here. It would be somewhere up in the ceiling, but then come down around the Planck mass very, very quickly. And I have not included this here, but it comes down somewhere here and would probably even meet two of the other 3. What that means, I don't know, but it may give us a hint that even something beyond grand unified theory should be in reach. Are there unknown forms of matter? Is our world supersymmetric? Not seen so far, but very much speculated about. What is the origin of dark matter and dark energy, which make up 95% of the energy and matter bill of our universe? We don't know all these things, and of course we hope to find at least dark matter candidates very soon. Yeah, another couple of questions is, and this is much closer to your field, is are there hidden extra dimensions? This is intimately connected to the question, why is gravity so much weaker than the other forces? Remember this 40 orders of magnitude between gravity and the strong coupling, and one could, as you know, one could explain this that in a 3+1 dimensional brane, which is our visible world, gravity is very weak, but it extends into other dimensions where it may be even as strong as the others. Yeah, I think the dark matter problem, for me at least personally, I think is one of the most thrilling subjects at the moment, because we are very close, hopefully, in principle, to find out whether there are dark matter particles and what they may be. There are certainly no standard model particles, so that means the universe is made of things which is not standard model particles, as we know, and so one may extend this little thing in English quite nicely. Our universe is made of stuff which is much more important than we are. We would like to know that, of course. Yeah, the most en vogue candidates to solve at least some of these problems, which I indicated. I just mentioned the 2 most prominent ones. Supersymmetry. It is fully compatible with and supported by grand unified theories. It also offers excellent dark matter candidates. The theory then becomes finite and computable up to the Planck mass, which is not the case for the standard model. It predicts basically nonsense much earlier than at the Planck mass. It is essential for the realization, as you know, of string theory, including quantum gravity. However, and these are minuses. No SUSY signal has been seen yet, neither at lab, nor at Tevatron, nor at any of the other preceding generations of particle accelerators. And I have a lot of experimental colleagues who since 30 years try to find SUSY signals and have not found anything. So that is not something one should laugh at. I mean, the attempts to do that are very, very far-reaching, back to the early days in particle physics at colliders. And so far nothing has been seen. And I personally ask myself, why should nature do such a thing? Hide something which may influence or dominate even the universe, but hide it such that we cannot see it, right? Maybe a philosophical problem. Okay, the second thing I want to mention here is extra space dimensions. It would solve the so-called hierarchy problem. It will bring down the Planck mass from its very high value to the order of 1 TeV. It is inspired by string theory, namely the compactified extra dimensions, which are claimed and necessary there. It offers exciting scenarios. However, it cannot solve many of the problems which I showed or mentioned in the previous slides. Not as such, not the extra space dimensions at all. And one also has to say there are enormously large model dependencies. You know that also in string theory, it is not a very predictive theory at the moment. However, in some cases, some predictions may be there where we find perhaps signatures at the LHC. Now, let me just mention for the future, there are two principal ways to search for new physics or for physics beyond the standard model. We have mentioned those. Of course, the direct production of new particles in highest energy collisions, suspecting that we have not seen them so far because their mass is so high. For instance, as LHC, two protons may collide, produce a squark and a gluino, two supersymmetric particles, which then decay cascade-like into the standard model particles, but always one supersymmetric particle, namely the lightest one, is remaining at the end, which would be the good candidate for dark matter. And the second big class of experiments for the future is indirect evidence from new phenomena in high precision experiments, so high energy versus high precision. Of course, the best is you have high energy and high precision, but that is pretty costly. Now, this high precision comes into the game through radiative corrections, virtual loops, and other things. For instance, here in E plus E minus annihilation to E plus E minus final state. With the zero exchange, you have virtual loops of top quark production there. Even if the top is much higher than the energy we have available at this vertex, they give corrections, and so does the Higgs. The Higgs, for instance, gives such corrections in E plus E minus collisions, and that is where the limits which we have talked about before come from analysis of such graphs and fits to the data. Now, this is a chart where I try to summarize at least the most obvious particle physics projects. It's by far not complete, but it gives us a good overview, I hope. Let's start with the high energy frontier, then we go to high precision. I have added neutrino beams, which is somehow not fitting, well, it's a class by its own, and then we have non-accelerator projects. High energy frontier, we have general hadron colliders and lepton colliders. You know most of them. Hadron colliders, we have the Tevatron, the LHC. Both are running. The Tevatron for a long time, the LHC just since recently. We have plans for upgrade for even higher energy or higher luminosity machines. One is called the high luminosity LHC, HL. This was so far what's called super LHC or SLHC. The name has changed due to the new direct at CERN. It's now high luminosity LHC. And there are also very recent plans of high energy LHC, which of course would, now high luminosity would talk about a factor of 10 increase in the luminosity, which one can do basically with the existing machine. For the higher energies, one would have to get rid of all these dipoles in the accelerator and replace them by even more powerful ones. We don't have such magnets now, but people seem to know how to build them, and in a couple of, let's say, 10-ish years, we may be ready to go for the next step. Okay, then lepton colliders. We had LEP. LEP is discontinued. It was switched off in 2000. And then we have bold plans. There's no running machine at the moment at the high energy frontier. The next thing which is discussed about since a long time, already 20 years, is the ILC, International Linear Collider, using superconducting acceleration cavities, which are known to to be made since 15 years or so. So one could build this machine, but it would be expensive. It would require an international effort, and so far nobody was standing up and saying that this should be built in our country. Germany has refused to do this, the government, and neither United States nor Japan so far have succeeded in finding consensus here. The next then could be CLIC. That's another, I will say a few words about CLIC. It's also an E+E- machine with a different acceleration technique currently being developed at CERN. And then for the long time future, of course, we may even think of building a muon collider, which would, if I have time, I don't have time, would be something like the ultimate machine we could at the moment dream of. Yeah, there's one collider which we had between leptons and hadrons, that is HERA, making very important contributions to the question of structure functions in the hadronic sector, and also look for new physics, nothing found. High precision experiments. Now there are high precision experiments with high energies, okay? These are the ones which are already there. These would all be also high precision because they use leptons. And then of course there is this whole stack of things at low energies, fixed target experiments, things like tau charm factory, B factories, which have been discontinued so far, but there's one, namely KEK, at KEK being planned for the future. Yeah, neutrino beams, long baseline, short baseline. I didn't go into neutrino physics, so I make this rather short here. There's quite a number of long baseline experiments, and there's a full new generation being planned, which is now called the neutrino factory, which may even bring us some clues in the CP violation leptonic sector, which may explain then finally the asymmetry of matter and antimatter in the universe. I don't say much about the short baseline experiments. One is still running here. And then there's, of course, a long list of non-accelerator experiments, like direct searches for dark matter. Very interesting topic. We may expect some results here, I heard, very soon. Axion searches, then measurements of neutrino mass, then neutrinoless double beta decay, then measurements of solar neutrinos, neutrinos from reactors, and neutrinos from space. I don't have time to go into these very interesting projects here, but you see there's a whole range of planned and even running or projects which are under construction. So you pick your choice, but you are all serious. You would not want to join any of these projects, as I understand, right? So LHC further plans very quickly. In 2010 and 2011, we will have continuous collision runs at 7 TeV, maybe ramping up to 10 TeV, but very, very likely not up to the full 14 TeV. This is excluded because we need some additional repair in the machine. The integrated luminosity is supposed to reach after these 2 years of 1 inverse femtobarn. Higher beam currents will then be reached, maybe also in these 2 years. When reaching the safe beam conditions, which means that the beam dump can be done in a very reliable, controlled way in the machine, because at high intensities, one beam dyed uncontrolled in the tunnel would destroy the tunnel, and by such also the LHC. So one has to be very careful there. The kinetic energy of the beam at full running conditions is like a fully equipped TGV at 120 kilometers speed. So that would be sufficient to really destroy everything there. First sensitivity for new physics will be reached. However, we will do mostly standard model physics comparable to the first 20 years of Tevatron, including the top quark. 2012, 1 year of shutdown, installation of full safety systems so that we can go to 14 TeV. And from 2013 on, we will have the full energy and the full luminosity, hopefully, available. And from 2017, we already started to plan an upgrade of the LHC to the high luminosity LHC, which particularly needs to upgrade also the detector for 10-fold luminosity. All right, expectations. Maybe I just leave this away for the first year. I just told you it's more or less standard model physics, which we can expect. So, and the first, maybe if we are lucky, first hints for supersymmetry, but this depends. Then the high luminosity LHC physics menu goes far beyond that. It goes to Higgs decay modes, where we can even measure the triple Higgs coupling, triple gauge coupling, supersymmetry, extended reach to many more TeVs, extra dimension, improved reach also for Kaluza-Klein states. and strongly coupled vector bosons, if there are those, and if there's no Higgs, should also be a topic for the super LHC. The high luminosity LHC would look, a typical event would look like that. You see it's a pretty big mess as this high luminosity, and the whole thing will be then a challenge for the detectors, namely for the efficiency and resolution and reliability. Yeah, linear collider. This is the ILC, possible sketch of the two linear collider arms and damping rings and the collision region. It will go probably only to half a TeV center of mass, maybe to something like 0.8 TeV. It will be made of superconducting cavities. It will be very expensive, $6.6 billion, only the machine, plus 13,000 FTEs. So at the moment, it's not clear whether it will be built and who will build it. The reach in precision can be viewed here. This is the mass of a hypothetical dark matter particle and the abundance of dark matter in the universe. This will be done by space missions, namely by the WMAP, which is the yellow band, and the Planck, which has just been launched. We expect results here. And the mass, of course, they cannot measure. This must be done by particle physics. The best case of LHC will be this bluish area here, and the ILC, if it will be built, would do a much, much better job in precision of mass and also abundance. Yeah, click two-beam scheme. I think my time is over. I should not go into details here. It's not done acceleration of particles by cavities, by the normal cavities, but by a drive beam at lower energies but high intensity, which will then be the electromagnetic fields will accelerate the second high energy beam. It will be even bigger, a 50-kilometer structure, 2 times 50 kilometer. It will be even more expensive. Not clear whether it will be realized. The center of mass energy will be a couple of TeV. A neutrino factory would do quite different physics. You need a very high intensity proton beam on target, make pions, let them decay into muons, to collect the muons, do a phase space cooling, all very rapid because muons don't live long, and then putting them into these accelerators. Once accelerated, they live a bit longer through the Lorentz factor, and then one can put them in such a shape where in these long sections they decay, and you have two intense neutrino beams, one pointing to Gran Sasso maybe, and one pointing into any other far detector, even on the other side of the world. Muon collider complex would be a step further. That's also CERN study. There's also Tevatron studies, of course. One would have a low energy neutrino factory pointing to the Gran Sasso. One would have a low factory Higgs, a low energy Higgs factory, muons directly producing Higgses. So one could do Higgs studies with very high precision, and then one could feed them at 2 times 2.5 TeV into the LHC, and then in a collider ring, which is even smaller. They don't radiate so much as electrons, so that is what makes them favorable. So we would be able to do almost all kinds of open questions with such a collider complex. However, technology is just not ripe. Let me stop with this slide. It is a political slide. We have, of course, a European strategy for particle physics. This is done by the CERN Council. In July 2006, they came out with this with a paper describing what would be the future of particle physics, at least in Europe. It looks similar as the studies done in other parts of the world. Highest priority is to fully exploit the physics potential of the LHC, that's clear, and to work towards an upgrade at around 2015. This will be already 2017 or 2020. We develop, of course, the technology for high energy E plus E minus lepton collider. We may, in between, build the ILC. This is a bit blue-eye-ish. I don't think the LS. My personal view is that an ILC will not be built. The time window is almost closing. There must be European participation in a global neutrino program. A very bold wish. No further much details. And there's a coordinated European strategy for non-accelerator experiments, of course, also ongoing. I should say that an update is planned for 2011 and 12. And there are similar roadmaps for the US and for Japan. And I think I should stop here. And if you have questions, you may ask me, of course. Thank you. Yeah, which project do you want to join? No question. Yeah, there's one question. Yes, I omitted many things. Yes, of course. Of course, that will be done. Yeah, that's okay. I think that can even be done in the first 2 years, in the running period now, such things. We will, and so LHC will exceed in almost any of these possible studies the significance of mass windows or windows of reach for new physics of the tevatron. It will, I think, exceed it, not by factors, but in many cases it will be a little bit better. Yeah, this is what we can expect by LHC.
You explained this, the gap between TEF and this lab data for the Higgs mass, so why it's short stretch?
Let's see. Come on. The best is I get this. Yeah, maybe I take this little. I take this little version here. You mean this gap?
Yeah, what is the original?
This is 100. The lowest limit is 114. This is the end of the direct searches. So it must be heavier than 114. Otherwise, we would have seen it at lab directly, right? And and then the radiative corrections tell us it must be smaller than about 200, 180. But this is a theoretical prediction, and depending, I think, on the amount of radiative corrections which are put in there. But one should take it half serious at least. And then this other yellow thing is also the exclusion from direct searches, and this is done by tevatron. And tevatron is sensitive only in the region where the Higgs mass is sufficient to let it decay into W plus W minus. So this little window they could exclude. And this is about 157 to 170 TeV. There's no direct signal. Yeah? So if the Higgs exists, and this is all for the standard model Higgs, and for most versions of supersymmetric Higgses, then it is most probably lying in this little white band, which is 114 to 160 or so. And I didn't show this to you, but this is a region which makes it also for LHC rather complicated because of huge backgrounds. The Higgs discovery is easiest also for LHC in the region where the mass is higher than 180. So higher than 180 here, because then the Higgs decays into Z0, Z0, and Z0 may decay in me plus, me minus. So one has 4 high energetic muons in the detector, which is a very, very nice, almost background free signal. At these low energies, the Higgs decays mostly into BB bar. And at the Hadron machine, you cannot detect all these hadronically decaying Higgses. So that makes it difficult and makes it necessary to run for a couple of years at LHC. But ultimately, this region will be closed in a couple of years, or something will be found. Okay, any more?
Why do you think that having neutrinos are unlikely?
Why do you think that?
That there are no heavy neutrinos.
Do I think that?
You said they are unlikely.
They are unlikely, yeah, well. We have 3 generations of neutrinos. They all seem to have masses which are in the EV range or less. Now, of course, in the quark sector, we also have the case that an up-down quark is so much lighter than a top quark. You may argue from that. We cannot exclude it, but personally, I mean, just from a gut feeling, I think it's unlikely to have 3 very low neutrinos and then the 4th one at very massive mass scales. But it's not excluded, of course. We cannot exclude it. Yes?
When you collide at 7 GeV center of mass energy,
Yeah.
do you lose any information about non-transverse there any improvement in measuring the center of mass energy of, say, parton collision?
I'm not sure whether I understood your question correctly. I mean, if we collide two protons and they collide head-on, then there is, if there's energy momentum conservation, there is no transverse momentum, almost no. I mean, the quarks which collide, they may have small transverse momenta.
So what you measure is, you can say that the final state has no transverse momentum.
Yes.
What about the other?
Oh, the longitudinal momentum we don't know, because we don't know which of the constituents of the two protons actually collide. Whether it's two quarks or one gluon and a quark, or two gluons, and we don't know their part of the energy and of the longitudinal momentum of the proton which they have at the time of the collision. So the coordinate along the beam is completely undetermined in the final state. We don't know anything of that. We only know the in the initial state. The final state we measure, and most events are concentrated to, they have, of course, transverse momentum, that is what we measure, otherwise you wouldn't see the particles, and they have a net longitudinal momentum. So the longitudinal momentum is mostly not zero. That means the two constituents having hit each other have different energies along the beam pipe. And this is unknown. This can only be done in a this can only be accounted for in a statistical way by parameterizing these structure functions, parton density functions in the proton. So for many, many collisions, we have some information where we know, mostly from HERA, what is the average energy of down-type or up-type quarks or gluons in the proton. And this can be used, but this is only on a very large statistical basis, not by event by event. So event by event, the longitudinal momentum is of no interest, basically. Yeah?
Does there exist any upper bound for mass effects?
Yeah, this is the 185 or so, which comes from theoretical fits to the electroweak precision data of lab. And in terms of the standard model with all the radiative corrections, there's an upper bound of consistency with the standard model for the Higgs mass of 185 or so. Yeah. But not for the supersymmetry. For supersymmetric Higgs, the phase space is of course much, much more open. But even there, I think there are theoretical arguments that the Higgs boson beyond 1 TeV mass makes no big sense. And actually in supersymmetry you have at least 5 Higgses. And there are pretty good predictions in the minimal supersymmetric standard model about the mass of the lowest one of those. And that should be fully in the reach of LHC, of course. So even there, for standard supersymmetric standard model, the Higgses, maybe not all 5 Higgses can be seen, but at least the lowest one should be found. Of course, it will be difficult then to decide if one sees something, is this a supersymmetric or standard model? That will take much longer, of course. So,
Another question.
Yeah.
What is the rate of prediction of Higgs in the LHC? I mean,
oh,
how much times we run the Higgs on one?
very good question. I omitted that graph, but I think I have it in my spare slides. So let me see. I think I have a graph like that. I didn't show the cartoon either. Ah, here it comes. Okay, this is cross-section of production of objects as a function of the center of mass energy. Now, LHC will run at 14 TeV, which is this white vertical line. 10 TeV is the middle one, and 7 TeV, where we are running now, is this left one. Tevatron is here. So we see the total cross-section of events which we see is very high. It is up here at 10 to the 8, and oops, there's some overlay of text here. 10 to the 8 nanobarns. While a Higgs, let's see, a Higgs with a mass of 120 GeV will have this line. Now you see a tevatron, this is 12 orders of magnitude, and we have a much higher chance at LHC where we are running now, and even at 14 TeV. But still it's 10 orders of magnitude below this total cross-section. So looking for a Higgs there is like looking for a needle in a haystack, right? I mean, it's one out of billions and billions of events, which may be a Higgs decay. And here is the number. This axis gives you the events per second for the full, almost the full LHC luminosity of 10 to the 33. This is still 3 orders of magnitude higher than we have now, and that gives you, for a Higgs of 120 GeV, gives you one event in every 100 seconds of running time. Yeah. So it's a very rare process, and the experimental art is in filtering out these events and not losing them. All right, I see more questions, right?
So let's thank